Welcome back, everybody. This is our second session in JEE mains previous year questions for chapter Electromagnetic Induction of class 12th. Before this video, we have made one video in this series, and that video is available on our YouTube channel's playlist section. We have also started similar series for NEET previous year questions, and those videos can also be found on the YouTube channel's playlist section. If you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount, however small it may be, will be highly appreciated. With this, let's start today's video. In the previous one, we completed up to question number 5, I think. This was the last question which we covered, and today we will move to the next one. So let me adjust pen thickness slightly. In a fluorescent lamp choke, a small transformer 100 volt of reverse voltage is produced. So we can say induced EMF is 100 volt. When a choke current changes uniformly from 0.5 ampere to 0 ampere in the duration of this time is given, so self-inductance we have to find out. Now we know that induced EMF, we have a relation for induced EMF, that is d phi by dt, and this can be further written as L di by dt. So we will use this relation here, that E is equal to di by dt. So induced EMF is 100 here, L as it is. Now di is change in current, that is 0.25, 0.25 to 0. We are ignoring the negative sign here because inductance is positive, so we are taking everything in the positive sense. Divided by the time, that is 0.025. So this will be 100 is equal to L 25 into 10 raised power minus 2 divided by 25 into 10 raised power minus 3, 25 cancelled, and from here we will get L is equal to this will be 10 raised power minus 1, and in crossing this will become, so one thing to notice, that time is in milliseconds here, so we will get additional 10 raised power minus 3. That the term I was missing. So this is 10 raised power minus 6, here it is 10 raised power minus 2, so in the denominator we will get 100 L divided by 10 raised to power minus 4. So L will be 100 into 10 raised to power minus 4 and 10 into 10 raised to power minus 3, and this is 10 millihenry. So we have to find in millihenry, so it will be 10. Now moving to the next one. At time t is equal to 0, the magnetic field of 100 gauge is passing perpendicularly to the area defined by the closed loop. So we have a closed loop, and there is a constant magnetic field, initially constant. If the magnetic field reduces linearly to 500 gauge in 5 seconds, then the induced EMF is. So let's first find out the rate of change of magnetic field. So initial magnetic field is 1000 gauge, final field is 500, and time it took is 5 seconds. So dB by dt will be change in magnetic field, that will be final minus initial, so minus 500 divided by 5 gauge per second, so it will be minus 100 gauge per second. Now we know that 1 Tesla is 10 raised to power 4 Gauss, or 1 Gauss is be 10 raised to power minus 4 Tesla, so it will be 10 raised to minus 100 into 10 raised to power minus 4 Tesla per second. So 10 raised to power minus 2 Tesla per second. This is the rate of change of field. Now we have to find the induced EMF, and induced EMF we can find using this method, that E is equal to d phi by dt, and that will be area times dB by dt, as area is constant here. So we have the value of dB by dt, so we have to find the value of area. Now this is a we can assume it like a rectangle. If we join these two sides, then this will be a rectangle, out of which there are two triangles which needs to be subtracted, and these two triangles will additionally, if we combine these two triangles, they will form a square. So we can say area of the full area of this complete rectangle including triangles will be 16 into 4, that will be 64 centimeters square, and area of this triangle will be half into its base, sorry, twice, because there are two triangles, into base, that is 2, and height is also 2, and we have similar triangle here, so also multiply by 2. So this will be 4 into 2 into 8, so it will be 8 centimeter square. So net area will be 64 minus 8, that will be 56 centimeter square. So substitution value here, 56 into 10 raised to power minus 4 into negative of 10 raised to power minus 2. Here negative sign just for the direction of the EMF. It will not decide the magnitude. It is just for direction or sign, positive, negative. So it will be 56 into 10 raised to power minus 6. So 56 into 10 raised to power minus 6, and it will be minus 156 microvolt. So option A will be the right answer here. Let's move to the next one. Consider a circular coil of wire carrying constant current I, forming a magnetic dipole. The magnetic flux through an infinite plane that contains the circular coil and excluding the circular coil is given by phi I. The magnetic flux through the area of the circular coil is given by phi node. Which of the following option is correct? Now to solve this, let's suppose we have a coil here. Okay, let's choose different color so that contrast is better. So suppose this is our coil and it is in the plane of the screen, in screen's plane or in the plane of paper. Now as this coil carries current, so suppose this is the direction of the current. This is the direction of current. So if we see from the above, then it is a clockwise direction. So magnetic field lines will go into the coil here. Magnetic field lines will go something like this, and then they will come behind, from the behind of the coil. Similarly, on this side, magnetic field lines will move something like this. Now it is mentioned that magnetic flux through the infinite plane that contains the coil, means suppose this plane contains the coil. This is the plane which is containing the coil. So magnetic flux through this coil is given by phi I, So magnetic flux through this whole plane is given by phi I. Now, uh, where does this magnetic flux come from? It comes from these magnetic field lines. The magnetic field lines of the coil, they are, we can say, going through the two areas. First area is inside the coil. The area inside the coil, the magnetic flux lines are passing through that area, and second area is outside of the coil. They are also passing through that area. And if we can see from this diagram that inside of the area, these magnetic field lines or we can say inside the coil, these magnetic field lines are going into the plane of paper, and outside this coil, these field lines coming out of the paper. Or we can simply get the direction of the magnetic field, that inside the coil, direction of magnetic field is into the paper, and outside the coil, direction of magnetic field is outside of the paper. So in the both area, in the area 1 and in the area 2, direction of the magnetic field is opposite. And we also know that direction of magnetic field is opposite, but magnetic field value will be the same, as this is due to the same field lines. So this is the flux. Outside flux is phi 1 and inside flux is phi node. Now direction of the flux depends upon the direction of the magnetic field, as inside the coil, the direction of the magnetic, we can say magnetic field lines is going into the plane. So if we consider into the plane as negative, then outside of the plane will be positive, and if we consider outside of the plane as negative, then inside the plane will be positive, and total flux will be equal because it is produced by the same source or the same ring. Only just the direction will be reversed. So we can say phi I is equal to negative of phi node, or phi node is equal to negative of phi I, and that is option D for us. Now let's move to the next one. A long solenoid of a radius r carries a time-dependent current. Time-dependent current is given. A ring of radius 2r placed coaxially near its middle. During the time interval 0 to 1, the induced current and induced EMF in the ring changes as. So we have to find, uh, basically we have to find expression for induced EMF and then for induced current, and then we will deal with the given options, that it remains unchanged or how it is changing. So first of all, let's draw the diagram. Initially, as mentioned, we have a long solenoid. So suppose this is our solenoid. We have a 3D representation here for solenoid. So suppose this is our solenoid. Suppose this is our long infinite solenoid. So for a long infinite solenoid, we know that outside there is no magnetic field because it is an infinite solenoid, and magnetic field is only inside, and that is also constant. Now we have a ring that we have placed coaxially with it with radius r. Now radius of this solenoid is r, and we have a ring placed with 2r radius. So we can say, suppose this is our ring which we placed over it of 2r radius. Now we have to find induced EMF in the ring. So to find the induced EMF in the ring, we know that what we have to do, induced EMF is given by d phi, negative of d phi by dt. and this flux is flux induced with the ring. So in this case, in flux we get magnetic field into area. Now magnetic field will be produced by the this solenoid which is carrying a current. So it will be, we know magnetic field for a solenoid is given by mu node Ni, mu node N, where N is the number of turns per unit length, I is the current, and coming to the area. Now this area here, area, as magnetic flux, magnetic field is only linked with only this part of the coil. Yes, this part of the ring, sorry, we can say a ring or coil. What is it? A ring. Only this part of the ring. Let me draw it in a sideways. Suppose this is our 2r radius ring. Then out of this 2r, solenoid is only passing through that much portion of the ring, and only in that much portion we are having change in the magnetic field. In the remaining portion there is no magnetic field, because outside a long solenoid there is no magnetic field. Magnetic field is totally confined within itself. So in the outside region there will be no magnetic field. In the inside region, only in this region we have a magnetic field. So we have to take area of only this much part, and that is pi r square. So pi r square. So solving this further, what we get, mu is constant, n is constant, pi is constant, r is constant. We have only I change as variable, so it will be negative mu node n pi r square d by dt of I. Now it, or dependence of current with respect to time, is given by I node t into 1 minus t, and from this di by dt will be given by I node as it is, differentiation of t 1, so 1 minus t is left, plus t into 1 0 minus 1. So this will be minus t, 1 minus t, so 2t. So we can write it like minus mu node n pi r square into I node 1 minus 2t. So this is the value of EMF, and from this we can find out the current will be EMF by resistance. So it will be minus mu node n pi r square. Here capital R is radius and small r is resistance, into I node 1 minus 2t. Now from this we can find out that when current will be 0. So current will be 0 when this whole expression reduces to 0, and this whole expression reduces to 0 when 1 minus 2t is equal to 0. So 1 minus 2t is equal to 0 means t is equal to 1 by 2. At t is equal to half, current is equal to 0 ampere, and after that what will happen? Initially 2 into t will be smaller than 1. So suppose current is flowing in the left direction, and after t is equal we can say after t is greater than half, or when t becomes more than half, then this term will become negative. So negative will become positive. So we can say current will change its direction at t is equal to half. T is equal to half, it will 0, and after that it will change its direction. So if we see here option D, then at t is equal to 0.5, direction of the IR reverses and VR is 0. And if we put t is equal to half here, then potential or induced EMF is also becomes 0. So option D will be the right answer here. So with this, let's move to the next one. A loop A, B, C, D, E, F, A of straight edges has 6 corner points. Corner points are mentioned and the magnetic field in this region is mentioned. The quantity of flux through the loop. So let me first draw the diagram. As this is a 3 coordinate system, 3-dimensional. So we have to draw a 3-dimensional diagram. So our first point is 0, 0, 0. So it is center. This is center point. Second point at x is equal to 5. This is B. Third point at x is equal to 5 and y is equal to 5. So this is C. Fourth point at y is equal to 5. Sixth point at y is equal to 5 and z is equal to 5. So it will be something here. And last point is at z is equal to 5. So let's join them. So this is the structure. And we have been given magnetic field here. And we have to find the flux. So value of magnetic field is 3I plus 4K. And let us assume to find the flux, if we need to find the flux, we have to take a dot product of magnetic field into area. And for that, we have to, what we have to do, we have to break these two loops. As we can say, this is a single loop of A, B, C, D, D, E, F. This is a single loop. So what we have to do, we have to break this loop into two individual loops with each loop in a single plane. Right now, of this complete loop, out of this complete loop, is its part A, B, C, D is in XY plane. Part A, B, C, D, A is in XY plane, and part A, D, E, F, A is in YZ plane. So we have to break it in a way that these two planes or these two loops comes separately, so we can do their individual calculations. So what we can do here, we will break this loop at two points D and A. So we will draw a line here like this and a line like this. Now direction of the current will be also decided. Suppose initially current was going something like this. Initially current was going something like in this loop. So that was the initial direction of the current. So what we have done, we have connected D and A. So from D to A in the YZ plane or in the plane A, F, E, D, A, current will go downward, and its opposite arm current will come upward. So these as a whole cancel each other. So now we have two planes, one in YZ plane, two loops, sorry, two closed loops, one in the YZ loop and one in the XY plane. So let's come for the YZ plane, or we can say flux for A, F, E, D, A. That will be magnetic field is for us 3i plus 4k dot product of the area. Now using the right hand screw rule, we can find the direction of the area vector here, and area vector will go towards the positive, let me use a different color. Area vector here will go into the positive x direction, as our plane is in yz plane. Oh sorry, our loop is in yz plane, so area vector can go either in the positive x or in the negative x. So according to right hand screw rule and according to direction of the current, we are taking in the positive x. So area will be, and side length is 5 for each, so 5 into 5, 25 into I, as this is dot product, so it will be 75 of I. This is flux for A, B, C, D, E, F, A. Now flux for second loop, that is A, B, C, D, A. For this again magnetic field is same, and for this the area vector, as this is in y-x plane, so its area vector according to right hand screw rule will go into the negative z direction. So it will be negative of 25 of k, and taking the dot product, it will be minus 100k or minus 100. So here I dot I0 minus 100. This is the flux for the second one. So net flux, if we calculate here, then it will be 75 minus 100, so it will be either negative 25, or depending upon the how we take the direction, that it can also becomes positive. So 75 plus 100 is also possible, so it can be either negative 25 or 175. But if we take according to direction of the current, then it will be negative 25. But both answers are possible depending upon the how direction of the current is taken. And if we even don't take the direction of the current, then both will be positive. Then that in that case 175 will be the answer. Let's move to the next one. A planar loop of wire rotates in uniform magnetic field. If T is equal to 0, the plane of the loop is perpendicular to the magnetic field. So plane of the loop is perpendicular to magnetic field. So again we can say, suppose this is our magnetic field, so loop is something like this. So that plane of the loop is perpendicular to magnetic field, means aerial vector of the plane is in the parallel direction with the magnetic field, or we can say A will be, as this is rotating, so A will be A node cos omega t. Now it rotates with a period of 10 seconds, so time period is given. We have to find magnitude of induced EMF, and at what time it will be maximum or minimum. So we know the time period. From this we can find out omega. Omega will be 2 pi by t, so it will be pi by 5 second. And suppose the value of magnetic field is B, so induced EMF will be negative of d phi by dt, so B into A, and from that we can say it will be minus d by dt. B, A will be A node cos omega t, so it will be my derivative of cos is sign, negative sign, so it will become plus B A node omega sine omega's value is 5 pi by 5 into t. Now EMF will be maximum when, as B A omega is constant, so it will be maximum when this term is maximum, and it will be minimum when this term is minimum. So for maximum, this term's maximum value is 1, sine's maximum value is 1, and that happens at pi by 2 degree. So, sorry, pi by 2 radian. For that, so means this whole term should be equal to pi by 2, or pi by 5 into t should be equal to pi by 2. From this, pi get cancelled and times comes out to be pi by 2 or 2.5 seconds. So this is the condition for maximum. Now for minimum, this term should be equal to 0, and if not 0, then should be equal to pi, because in a sine we have curve like this. So sine gives maximum value at 0 radian or at pi radian or at 2 pi radian. So as 0 is not mentioned here, so we will go to the second one, that is pi radian. So pi by 5t is equal to pi, and from this times comes out to be 5 seconds. So option B will be the right answer here. So with this, we end this video here. Hopefully whatever we have covered is helpful to you and understandable also. Again, if you have any doubts or suggestion, then you can put them in comment section. I will try to resolve them. And if you find this video helpful, useful, then do press the like button, share it, and subscribe to our channel. And if you want to donate us something, you can scan any of these QR codes. Any amount of help will be highly appreciated. With this, again, thanks for watching, and we will meet in next video.